Another Coulomb's law example. This one's going to be a vector example, page 498, number 13. It says a charge of 6 millicoulombs is placed at each corner of a square 1 meter on a side. Determine the magnitude and direction of the force on each charge. So basically you have 4 corners of a square with a 6 millicoulomb charge in each corner. And the distance is 1 meter this way, 1 meter, 1 meter, 1 meter. We're going to find the net force on the left corner charge. If you think about it, these are all positive charges, so they all want to repel each other. So the left corner charge is going to be pushed, basically up and to the left, and as you'll see. So let's number these charges. This is charge 1, charge 2, charge 3, and charge 4. So 2 is going to push 1 to the left in this direction, F12. Then 3 is going to push 1 upward in this direction, we'll call that F13. And 4 is going to push 1 at an angle like this, F14. Okay, so we'll use Coulomb's law to find the magnitude of the force for each of those and then add them as vectors. So F12 is going to be K, which is 9 times 10 to the 9th, times 6 millicoulombs, which is 6 times 10 to the negative 3rd. And it's the same thing again, so I could have wrote squared if I wanted to. Not this time, though, because I already wrote it twice. And divide by the distance is 1 meter squared. All right, so if we punch that in the calculator, we get 9e9 times 6e negative 3 times 6e negative 3. Yeah, 324,000 newtons. Seems high. I'm going to check that. Oops. No, I get the same number. Okay. Now, it should be obvious that F13 is going to be the same force in magnitude because it's the same distance away and it's the same amount of charge. So we end up with the same magnitude. Now, F14, though, is not going to be the same because the distance is different. So we have to find this distance here. Well, if you think about it, it's a right triangle with 2 legs, each of side 1 meter. So you can use the Pythagorean theorem and end up with this distance being the square root of 2 meters, which is 1.4. In any event, we calculate F14. It's 9 times 10 to the 9th times 6 times 10 to the negative 3rd times that again, and divided by the distance is the square root of 2 meters, but we square that. Okay, so basically you're going to end up with half of what you had the first time, if you think about it. 162,000 newtons. Okay, so I have 2 forces that are this much, 324,000, and then I have 162,000. Now I can't simply add or subtract them algebraically because they're not in the same direction. So what we're going to do is add them as vectors, and I'm going to draw that out here. Okay, so what we have is we have 324,000 newtons to the left plus another 324,000 newtons upward plus 162,000 newtons at a 45-degree angle up and to the left. So it makes sense here to choose positive directions to be upward and to the left. And I'm drawing that out here. Okay, so what we do, since we're adding vectors, is break it up into x and y components. The first vector's x component will be positive 324,000, and the y component is 0 because it doesn't go up or down at all. The second vector has no x component because it doesn't go to left or right, but the y component is 324,000 newtons. And then the third one, we're going to have to use trig. So we're going to break this up into its components using sine and cosine. So the x component will be 162,000 times the cosine of 45 degrees, which is 114,551. And the same thing for the y component since it's 45 degrees. So now I'll find the resultant here. So I have plus 324,000. 438,551. 438,551 newtons in each direction here. 38551. Okay, so the x component is positive, so it goes this way. 438,551 newtons. And then the y component is also positive, so it goes 438,551 newtons. So we need to find the hypotenuse in this direction. We know this angle obviously is 45 degrees since the legs are the same size. And then we'll do 438,551. 620,205. 620,205 newtons is the net force directed at a 45-degree angle up and to the left. So it's a little more complicated example using vectors.